In this question, what is a truth table? What's DeMorgan's law? And what is Boolean simplification? Well, a truth table is actually fairly straightforward. If we say that A and B are all the possible combinations, I should say actually all the possible Cartesian product of true and false, then what different operations can I perform and what do those outputs look like? Well, I can say A and B, and I end up with this result. And notice this pattern, true, false, 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 right? So when A and B are both true, I get a true. However, if they're not both true, I get false back. What about OR? Now in Python, this is the inclusive OR, right? So we get a true, 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 false pattern. So when either A or B are true, or in addition to, I should say, when they are both true, we get true as a result. The only time that OR gives us a false back is if both A and B are false. And now we can go through and do this with the rest of our operations, our not, right, which is the negation of A. So this is a way of saying our result does not depend on B at all. Instead, it's just not A. And in this lower data frame, we have the exclusive OR. So it's the same thing as the inclusive OR, except we also don't evaluate to true on this top statement. And so truth table are just the different ways that functions can represent their inputs. What are all of the different ways we can combine them? And before we go into that, I wanted to discuss DeMorgan's law, conjunction and disjunctions, the fact that there's just many ways to represent the same expression. And so we have this idea of NAND. And when we talk about logic in Python, we can just represent this as a not A and B, right? So if we take A and B and then we just invert that truth table that we saw before, we can get a result of NAND. However, what's very interesting is NAND can be represented in multiple ways. It's not just not A and B. NAND can be inverted, or we can apply DeMorgan's law to NAND and essentially say, this is DeMorgan's law, the negation of a conjunction is the same thing as the disjunction of its negations. And so when we talk about conjunction and disjunctions, this is a conjunction, right? A and B is a conjunction. A or B is a disjunction, right? So we can use these terms kind of interchangeably here. However, if we apply DeMorgan's law, we can rewrite not A and B as not A or not B. But let's go ahead and test this out, see if it works. We can see here in the left-hand column, I have our original NAND function. Then in the right-hand column, I have my DeMorgan's version, or DeMorgan's law applied version of NAND. We end up with the same pattern of results. And when we're looking at this truth table, if two things have the same pattern of results, we conclude that behaviorally, they are the same function. And we can do this we can invert this too. Earlier I said the negation of a conjunction is the same as the disjunction of the negations. Well, we can invert that. We can also say the negation of a disjunction is the same thing as the conjunction of the negation of both of the elements. And so when we apply this law, we also see that we get the same output. And this is just to say that NOR and this DeMorgan's law converted version of NOR are the same. What this tells us is there's many different ways that we can write the same Boolean logic that achieve the same outcome. And so when we think about this, we can actually denote these formulas, these expressions in different ways. We can convert things to their conjunctive normal form. And so if we take this expression of not A or B, and then or D, right, and we want to expand this out a little bit, well, we just apply DeMorgan's law. First, we simplify this left-handmost expression, right? This is the same, that's that negation of a disjunction right there. And so we know that this expands to not A or not B. And then we have this or D to deal with, and we can actually apply one of our commutative properties in order to distribute that D. Essentially, if you're familiar with distribution in algebra, you can distribute that D, and we end up with our conjunctive normal form. What is conjunctive normal form, though? Well, conjunctive normal form is the idea that we can rewrite almost any expression in terms of ors and ands, where each of our phrases, each of our smaller terms, right, are joined by an or, and then our larger terms are joined by an and. And so you can see that here in our conjunctive normal form, we have D or A parenthesized, we have D or not B, I should say not A, D or not B parenthesized, and these parenthesized values are joined by an and. On the flip side, we have disjunctive normal form, which are and terms joined by or. And you can see here, although our inputs aren't the exact same, these both provide very nice examples of conjunctive and disjunctive normal forms. We can rewrite this expression here into its disjunctive normal forms, where each term is joined by and, within each term is joined by and then across the terms, right, we joined by or. Now, say we have a specific output. Say we have this truth table, right? Now we have 3 variables, not just 2. We have A, B, and C, and we have 8 different outputs. How do we go about deriving, right, what expression that was applied to these 3 inputs? Well, first, we can do a little bit of data manipulation, and this should be a 3-dimensional representation, but I'm using a pandas multi-index to convey the same information. But we start by unstacking C, so we end up with more of a 2-dimensional table. This idea of using Karnaugh maps for deriving the functions are all about paring down the number of dimensions that your input has, right? If your input has 4 variables, you have 4 dimensions, you want to process that into a 2D structure. This is typically something that you'll apply using handwritten notes. You would actually draw this table out, but I like using pandas, so I'm going to show you here with pandas. We expand our final dimension C into the columns of our table, and then we perform one more change. We actually swap on any row or column that has 2 or more nested variables in it. We swap the last 2 rows. So if our column were to be nested as well, we would also swap our last 2 columns. But what you can see here, and I'm using iloc to do this, right? Swapping the last 2 rows. And then what we do is we look for groupings of 2, 4, or 8 true values, or ones in this case. And so I'm looking for immediate adjacent, not diagonal, groupings of 1. And what you want to do once you've located a grouping of ones, you look for the variables that remain constant across that group. So for this group of ones, I see that variable A goes from false to true. So I don't care about variable A. I don't think that variable A predicts this grouping as all, because variable A changes and our output doesn't change, so I don't care about it. But variable B stays true, and variable C stays false. So what I would do for this grouping, I start out by writing my formula as B and not C, right? And this is because C is false, but our output is true, so that's how I know it's not C. And then, that's my first term. I join this with another term that will be represented by a disjunction. And in my next grouping that I find, I see here in this bottom row, there's another grouping of 2 ones right next to each other. I then do the same process. Well, what stays the same and what changes? A happens to stay the same. A stays the same, right? So since A does not change and A is true, I just write down the term A. And I see that B stays the same as well, but B is false, so I have to represent that with a not. And then when I look at C, I see, well, C changes from false to true when moving from 1 to 1, so we don't care about C. And so what we can do is we've written out this formula. What we want to do next is obviously test our conclusion. We want to test it back. And so what I'll do here is use a little bit of pandas eval magic, and I'll give it this same expression that I've written out up here by hand, and I will pair it right next to my original output column, and we can see here that my new test column has the exact same output. And this is one of the ways that you can go about reasoning how to derive, right, an operation from a set of Boolean results. You can also use a little bit of logic to then simplify some of these operations. Right now we've done deriving, we've gone over DeMorgan's law. How do we actually apply these in a meaningful way? Well, if we start off with this expression, not P and Q or P, we can apply DeMorgan's law, right, This is a negation of a conjunction, and according to DeMorgan's law, right, that's the same as a disjunction of its negation. So we expand this a little bit. This is Boolean algebra, right? If you've ever simplified an algebraic expression, x squared plus x plus anything, if you've simplified that into its terms, this is the same idea, simplification via algebra. So we apply DeMorgan's law, and we get this next step. We can apply a commutative law, and all this allows us to do is say, well, since these are all joined by or, the ordering of things doesn't really matter. That's like saying 4 times 5 times 3 is different or is the same as 3 times 5 times 4. It doesn't matter what order I multiply these in. And so I'm actually able to remove this parentheses. I'm able to put P and not P next to each other. Those end up always be evaluating to true, right? P or not P, well, no matter if P is false or P is true, that will always evaluate to true. So we end up with this expression of true or not Q. Well, true or anything will always be true. And so we end up simplifying this expression all the way to just true. And we can verify our check using SymPy's amazing simplify logic function. And we can see that when we feed this expression in, it evaluates to true. Meaning that if we had an if statement that looks like this, if not P and Q or P, this if statement will always be hit. It may as well not exist, and if you have an elif following up after it, this will never be reached. This elif will never be reached because the if statement will always evaluate to be true. So I thought, how can we apply this? What does this mean in practice? Well, if we take any expression and we can feed it into SymPy simplify logic to do the simplification for us, what is stopping us from doing this ourselves on actual Python if statements? And you can see here I've taken another formula, I've run the entire truth table on it, I've taken its original form and its simplified form and just shown that it produces the same result. We're now dealing with less terms and smoother logic. But what if I wanted to apply this to our control flow statements? Well, we'll have to first reach for something called the abstract syntax tree in Python. All this is doing is representing the code we've written as a series of data structures. And so you can see I have this simple code here. Define a function called add1. It takes input x and it returns x plus 1. And then I call that and I store it in the output variable y, and then I print y. If we look at the abstract syntax tree produced from this, well, we have a module, which is just a Python file. And in that module has a body. Okay, so in the body, we have, our function definition, which was our first line. That function was named add1. It took arguments, didn't take any position-only arguments. Those are the PEP 335, I believe, position-only arguments. No, sorry, 584, that's more recent. PEP 584 position-only arguments. But it does take regular arguments. That argument was named x, and all that function did was return x plus 1. And so in that function body, we see a return operation, which has a value of a binary operation, right? And that's going to be some add, subtract, multiply, divide. And what that does is it loads a variable named x on the left-hand side. It has an operator between them called add. And on the right-hand side, it has a constant of 1. That evaluates to return x plus 1. And so we can take this abstract syntax tree, and we can actually apply logic to it. If I define a node visitor, this is just something in Python's AST module that at every if statement, I can actually break down and view the code inside. I'll take that node that we've hit, that if statement, and I will simplify it using SymPy's simplification. And then I will actually rewrite I'll take the old code and the new code and I'll unparse them. This is essentially converting that abstract syntax tree structure back to actual strings or lines of code. And what we can do here, when we run this on this input here, if I take this code, now this could be written in another file, right? And you can load it in very easily. But if I have a branching condition with all of these conditions, I can check them with SymPy and I can see, is there an easier way to write this? Well, in the case, 4 out of 5 cases say, yes, we can write this an easier way. And in fact, we can see here that since this always evaluates to true, none of these other branches will ever be hit. So we can use this idea of simplifying our Boolean expressions to not only simplify our code, but also check for logical bugs. If our branching statements are not being hit, most likely this is not intentional. So what we can do is if this were stored as some type of pre-commit or something of that nature, you could use this tool as something very useful to figure out, well, does my code have any logical bugs in its control flow, in its if-else statements? And so there's a very neat way that we can apply logic, we can apply Boolean algebra to simplify that logic, and we can inject that directly into our Python code.